Okay, so you'll recall in the previous video where we looked at approximating areas under curves and how that sort of leads us towards the definite integral having a connection to area under curve. You'll recall that we sort of established by the end of that video that if we've got the integral from a to b of f of x, that does represent an area under the curve. So if this is y equals f of x, does represent the area under that curve between x equals a and x equals b, as long as f of x is bigger than or equal to 0 for x between a and b. Okay, so we want to think a little bit, we want to work on, in this video today, calculating some areas under curves using integrals. But we also want to think about, okay, well, what would happen though if the function was underneath the x-axis between a and b? So if f of x was less than 0, less than or equal to 0 for a to b, or if it crossed the x-axis. So we want to give that a bit of thought before we then launch into calculating areas using integrals. So I want you just first of all to evaluate the definite integral. And this is another point I want to make. I want you to be really clear about whether a question is asking you to find an area or evaluate a definite integral. Find an area, your answer should be in square units, definitely should be a positive answer. If you're finding a definite integral, the answer doesn't have to be positive. It's not suggesting that the integral represents an area, okay? And it also wouldn't be square units. Okay, so let's have a look at evaluating this. So nice simple function, x plus 1. Anti-differentiating first, so antiderivative of x is x squared on 2, plus the antiderivative of 1 is x, and we're integrating that between -4 and -2. So we know we substitute -2 in first, so that will give us 4 on 2 minus 2, and we subtract and we sub in -4. -4 all squared is 16 on 2 minus 4. So what have we got there? That's 2 minus 2, so that's 0, minus, this is 8 minus 4, that's 4. So we get -4. Okay, so clearly area isn't negative, so this doesn't directly correspond to an area. Let's have a look graphically at what's happening here. So this is the line y equals x plus 1, which is the function we were integrating, okay? And we're looking at between -4 and -2, which were the limits we had on the integral up here. Okay, so we want to think about, well, how does this integral connect with this area? Okay, so let's calculate that area, but let's do it using the fact that it's a trapezium, or we could do a big triangle minus a small triangle. Regardless, so when x is -2, y is -2 plus 1, so -1. Oops, sorry, so that means that distance there is 1. And when x is -4, y is -3, and so that distance there is 3. This is obviously 2 here, so what we have here is a trapezium. The parallel side lengths are 1 and 3, the height is 2, and so the area will be half times the sum of the two parallel lengths times the height. Half times 2 is just 1, and so we just have the bracket 1 plus 3, which is 4. So the area is 4 square units, but when we evaluate the definite integral, we get -4. Okay, so it's really important that we understand that if the region is underneath the x-axis, the integral will give us a negative value. So for regions below the x-axis, they have negatively signed areas. And so if we have a region below the x-axis, then we need to calculate its area using the negative of the integral. Now the other way you can do that, which is often a more efficient calculation, obviously, and we've talked about this with our properties of integrals, we know if we flip the terminals around, we get the negative of the integral, and so it would be the same as doing the integral from b to a of f of x with respect to x, rather than doing a negative, rather than having to subtract an integral. Okay, right, so it's really important that we understand that if a region is below the x-axis, its area is equal to the negative of the integral. Okay, now that isn't to say you couldn't calculate this definite integral and then say therefore the area is +4, but you need to be really careful about what you write. You should certainly not be saying area equals this and then magically turning it into a positive at the end. Okay, so just watch what you write. I would recommend that you actually set up an integral that equals the area to start with. Okay, so then let's think about, well, what happens if the region we're interested in crosses over the x-axis, so some of it's above and some of it's below. So the first part of this question here, we want to find the definite integral from -4 to 0, okay? So we want to integrate x plus 1 from -4 to 0. Okay, so we've already worked out this antiderivative, x squared on 2 plus x, and this time we're doing that between -4 and 0. So subbing in 0 will just give us 0 plus 0, subtract, and sub in -4 gives us 16 on 2 minus 4, which is 8 minus 4, which is 4, and so we've got -4. Okay, so again, we don't change that to positive. It's not, if the question doesn't ask us for an area in part A, we're just asked to evaluate the definite integral. When we evaluate this definite integral, the answer is -4. Fine. Okay, part B, we want to find the shaded area. Okay, so let's have a think here. We can see we can just do two separate triangles. So this distance is 1 and this distance is 1. This is obviously 3, and you'll remember this point is -4, -3, so this is also 3. Okay, so the area is going to be sorry, we're not going to do an integral, it's just going to be two triangles. Half times 3 times 3 for the big triangle, minus half times 1 for the small triangle. So that's 9 on 2 minus 1 on 2, which is 8 on 2, which is 4. Okay, so the shaded area here, apologies, I just realised I've made a mistake, and that's actually, it's an important one that we'll come back to because we shouldn't have got the same answer here. We're finding the total shaded area, so we're not subtracting this smaller triangle from that bigger triangle, we're adding it on. So it is 9 on 2 plus 1 on 2, so it's 10 on 2, which is 5 square units. Okay, so what we need to be really clear about here is just evaluating the definite integral doesn't actually give us a number that is directly connected to the area. So it's not just about just sticking a negative in front and being done with it. And that's because, and it was revealed a bit in the error that I made, because what we saw is I actually took away this area from the bigger triangle. So what I actually worked out was what that area is. Okay, and what we're actually seeing, which was an error, but that's what's happening essentially here. What it's saying here, what it's calculating here, is it's working out that this area here is negative, well, not area, but the integral there would be -9 on 2. This is positive 1 on 2, and so therefore, if I just integrate from -4 to 0 without thinking about the fact that the graph crosses the x-axis, it adds those two things together and it gets me -8 on 2, which is -4. Okay. But if we want to actually calculate the shaded area, we need to be mindful of the fact that part of this area is below the x-axis and part of this area is above the x-axis. And so if we wanted to calculate this area using integrals rather than triangles, it would be the negative integral from -4 to -1 of x plus 1 plus the positive integral from -1 to 0 of x plus 1, and we would need to evaluate it as two separate integrals. Obviously, we could also write this, if we want, as going from -1 to -4 rather than putting the negative sign out the front, and that's perfectly okay. Okay, but regardless, we have to actually evaluate two separate integrals if our area crosses over the x-axis, because we need to be able to think separately about the areas under the x-axis as being negatively signed. So, for example, here, this particular function, if we wanted to know that shaded area, the area that the curve is bounded between the curve and the x-axis, we would need to split it into two integrals. A positive integral from a to b, and then plus a negative integral, so minus an integral from b to c. The other way we could write that, obviously, would be to add the integral from c to b. Okay, so instead just flipping the limits around to calculate essentially a negatively signed area. Okay, so the key though is you've got to look at the graph. You have to have a look at a graph of what area am I trying to find here so that you can work out what integrals you need to set up in order to find that area. Okay, so let's work through some examples. Calculate the area of the region bounded by y equals x squared minus x equals 0, and x equals 3, and the x-axis. All right, let's focus on drawing this most complicated of the functions. So that's a parabola. If we factorize it, it's x times x minus 1, so it's got intercepts at 0 and 1. Okay, so I'm going to draw it on a particular scale for a particular reason. Okay, so we've got that essentially. Y equals x squared minus x, okay, and we want to find the area bounded by that curve, the line x equals 0, which is the y-axis, x equals 3. So if this is 1 here, this is 2 and this is 3. Okay, so there's x equals 3. Sorry, let's just continue that up there. And the x-axis, which is this line here. So we've essentially got curve, horizontal line, and x-axis. So any region that is bounded, so completely enclosed by those combinations of lines, so that is this bit of area here and this bit of area here. Okay, so we want to calculate the area. Let's set up appropriate integrals. So the area is going to be, so the first bit between 0 and 1 is a negatively signed area, so it's under the x-axis. So we're going to need the negative integral from 0 to 1 of x squared minus x with respect to x. And then we have a positive region, so plus the integral from 1 up to 3 of x squared minus x. Okay, so now in fact you can actually do a couple of things with the negative out the front. If you want, you could put it in here and make it x minus the positive integral of x minus x squared, or as we know, we could also make it a plus and switch the limits around. Okay, personally I do prefer to rewrite it without negatives out the front. I think it's really easy to kind of miss negatives along the way in your calculation, so I will probably write this as the integral from 1 to 0 of x squared minus x plus the integral from 1 to 3 of x squared minus x dx. Remember, don't forget your dx's. Okay, let's work them out. Antiderivative of x squared is x cubed on 3 minus antiderivative of x is x squared on 2. We're doing that from 1 to 0. And then we have plus, so it's the same antiderivative. We can just get that out of the bracket. And we're doing that from 1 to 3. Okay, so subbing in 0 first here, that's the upper limit. Okay, so 0 minus 0. Subtracting, subbing in 1, that will be 1/3 minus 1/2. I would really encourage you in doing these sorts of integrals by hand. As I've mentioned previously, you get a lot of fractions because of the way the process of integration generates a lot of fractions. And I'd really encourage you just to try not to skip too many steps in these. You won't make mistakes because you don't know about integrals or because you don't know how to set up the right integrals to find the right area. You'll just make numeric and algebraic mistakes. So write more steps down, try not to carry too much in your head, be really clear about what's happening. If you've got more steps written down, it also helps you to be able to check back through it, that you can actually see what you did. Okay, second one, let's sub in 3. So that's going to be 3 cubed is 27 on 3, so that's 9, minus 3 squared, which is 9 on 2. And then subtract, and we're subbing in 1, which is 1/3 minus 1/2. Okay, so we've got negative 1/3 minus 1/2. Let's get a common denominator in there of sixths. So that's 2/6 minus 3/6. Then we've got plus 9 minus 9 on 2. So that's 18 on 2 minus 9 on 2. So that's 9 on 2. Okay, and then we've got minus. Now this is the same. This one's the same as this one. Okay, so they don't cancel out though because they're both negative. But again, it's minus 2/6 minus 3/6. Okay, so 2/6 minus 3/6 is negative 1/6, and with the minus out the front, it's going to be plus 1/6, plus 9 on 2, and then the second, the final bracket's also, plus 1/6, because we're subtracting negative 1/6. Okay, so we've got 2/6, which is, I'll leave it as sixths because 6 is a nice common denominator here. 2/6 plus 27/6, multiplying top and bottom by 3 here, so we have 29/6. And it is an area, and so that is square units. Okay. So the shaded area here is in total, the two regions combined, 29 on 6 square units. Some people like to sort of do area 1 and area 2 and calculate 2 separate integrals and add them together, and that's fine. Personally, I think it's sort of valuable to be able to think through what the area will be equal to, but that's up to you. You can do them separately if you need to. Okay, this one here we're going to use our CAS, and the trigger here is that it says correct to 3 decimal places, so you couldn't be asked this particular question in a tech-free paper. We want to calculate the area of the region bounded by y equals e to the negative 2x, y equals x, and x equals 4, and the x-axis. Okay, so again, first thing is to sketch it and work out what region you're talking about. Okay, so we've got e to the negative 2x, so that's a exponential being reflected in the y-axis and a bit of a dilation, so it's going to go that way. Y equals x, horizontal line, x equals 4, vertical line, and the x-axis. All right, so let's plot what's happening. Okay, so when x equals 0 here, y will equal 1, so it's got a y-intercept at 1. Might just make it higher up just so we can clearly see what's happening. Okay, so that's the point 0, 1. That's the exponential. Then we've got the line y equals x. Probably didn't need to extend it that far. Y equals x. And then we've got the line x equals 4. Now, given that, just in terms of where that goes, given that this is, obviously you've got your CAS, you can check, but given that that is, the y-intercept of the exponential is 1, and that's the line y equals x, that would also be 1, and so therefore 4 is definitely further down over here. Okay. Alright, I'm not going to draw it perfectly to scale, but we certainly get the sense that 4 will be somewhere over here. X equals 4. Okay, so we want the area of the region that is bounded by those, and the x-axis, those 4 things, okay? So that line there, the curve there, the line x equals 4, and the x-axis, okay? So this region over here is not bounded by those 4 lines. There is a bounded area if we had the y-axis, okay? But it's not actually bounded. So the region that's actually bounded by those things is going to be this region in here that I'm shading. Okay, so in terms of setting up integrals to find these areas, we've got to recognize that it's actually 2 separate regions. It's under 2 separate curves. So we need to be able to work out that point, because between here, well, we could just calculate the area of a triangle with this bit, okay? But it is the integral under the line y equals x, whereas this bit out here is the integral under the line e to the negative 2x. Okay, so we need to know what that point is before we can set up the integrals. Okay, so we need to know the point of intersection, which is where e to the negative 2x equals x. Now that's not an equation we can solve by hand, which is why this is a CAS question. So we're going to solve e to the power of negative 2x. Sorry, don't know how I accidentally typed an F there. Right. Brackets galore. Let's try again. E to the power of negative 2x, and we want that to be equal to x, and we're going to solve for x, comma x, and we get x is 0.4263. Now we want our final area answer to 3 decimal places, so we don't want to round this point to 3 decimal places and then use a rounded answer to 3 decimal places to create another rounded answer again to 3 decimal places. We want to maintain more accuracy, and in my CAS I'm going to actually, type that value as accurately as I can, but certainly more than 3 decimal places. Okay, so the area, the shaded area, the red area, the whole lot, is going to be equal to, so the blue bit, which is the integral from 0 to 0.4263 of y equals x with respect to x, and then we're going to add that together with the green area, which is the integral from 0.4263 up to 4 of e to the negative 2x with respect to x. Okay, so let's get our CAS to evaluate that, correct to 3 decimal places. So we're going to do shift plus for an integral, 0 up to, I'm going to type this number in, 0.42, it's copy paste here. You could copy and paste it, then you have to go back and delete the x. So you could copy and paste the nice exact answer. You have to go back and delete the x. I'll do it this way, and then I'll show you that if you just typed in the 6 decimal places there, that would be more than enough accuracy to get your final answer accurate to 3 decimal places. I'll work it out exactly first, and then I'll sort of show you that it's the same. Okay, so that's the first integral, and then it's plus shift minus, shift plus integration from that x value. Now this is one of those copy paste problems. If I press, so you see my cursor is currently in the bottom of the integral. If I press up, my cursor now goes into this box, and if I press up again, it's going into the top of the integral, the upper limit, and then up here. If I were to press enter at this point to copy that answer down, it would go back, it would go to where my cursor last was, so it would go into the upper limit, okay, the upper terminal, which is not where I wanted. I wanted in the bottom one. So if I do want to use it, I can press Control C to copy this number here, and then I can go to where I want and press Control V. Again, I'm going to have to go back and get rid of the x equal at the start. So it's all a bit fiddly, where just typing it out to 6 decimal places would have been quicker and more efficient and just as accurate in this case, I think, but I'll confirm that for you. Certainly, if you want an answer to 3 decimal places and you're working accurately to 6, it should be more than enough accuracy. Okay, so that's my 2 integrals. My answer, therefore, my area to 3 decimal places is, 0.304 to 3 decimal places. It's an area, so square units. Let me just show you that if I had actually just typed in this number, which if I typed in what it said above, it would have been 462303, so it was rounded to 6 decimal places. If I do that over here as well, just so you can be confident that using 6 decimal places is more than enough to get an accurate answer to 3 decimal places. So 3.304 as well. Okay, so I would say that in that instance, trying to copy and paste and use that exact answer in those 2 different limits of the integration is actually much more fiddly than just if I just typed out 0.4263003, which is what I would have done. Okay, so all done. Let's have a look at another one. Sketch the graph and calculate the area of the region bounded by the curve and the x-axis. Okay, so we have a cubic graph here. Okay, it's a negative cubic. If you were to expand it out, you would have negative x cubed. It's got x-intercepts at 0, 2, and negative 2. Okay, so we should be able to plot that without too much calculation, with all the information that we need to be able to find the area. Okay, so that's the equation. Negative cubic, x-intercepts at negative 2, 0, and 2. Now remember, the question's not asking, well, it does say sketch the graph, but it's not really about, you're not earning lots of marks here. That's just a prompt so that you can find the regions that you need to, that you're trying to find the area for. So it's not about perfectly precise finding all the turning points. It's really just about sketching the graph to give you enough information to find the area of the region that we need. So we want the area of the region bounded by the curve and the x-axis. Okay, so x-axis and curve. There are 2 separate regions that are both bounded by the x-axis and the curve. Okay. Now, one of the things we want to look at when we're finding areas when we're integrating is to make use of symmetries to try and minimize the number of integrals we need to calculate. So in this particular case, so I'm just checking how much space I've got. Yeah, I'm going to write underneath. So in this particular instance, the area would be the negative integral from negative 2 up to 0 of x times, well, we're also going to need to expand that out to integrate it, so let's do that. Let's think a bit about this. This is actually 2 plus x times 2 minus x, so that's a difference of 2 squares. So this is x times 4 minus x squared, so it's 4x minus x cubed. Okay, so integral of 4x minus x cubed, so that's the negative region, the region below the x-axis, and then we would add that together with the integral from 0 to 2 of 4x minus x squared, which is the region above the x-axis. However, what we should notice here is that this is a symmetric graph, okay? This area below the x-axis, so if I highlight it in green instead, this green area is the same as this blue area. Now, mine doesn't look perfectly the same, my graph's not perfectly symmetric, but our knowledge of the functions tells us that those are the same. And so therefore, actually a quicker way to find this would just be to do 2 lots of that. I wouldn't use the negative one, so I'd do 2 lots of the positive region. So we could also just do 2 lots of the integral from 0 to 2 of 4x minus x squared. So looking for those symmetries where you can reduce the number of integrals that you need to calculate. So 2 times antiderivative of 4x is 4x squared on 2, so that's 2x squared, minus antiderivative of x squared is x cubed on 3, and we're finding that between 0 and 2. So 2 times, now careful here because it's 2 times everything, okay? So be careful that you don't end up just doing your first substitution and ending up only doubling that bit. So 2 times everything, okay? We're going to sub 2 in first, which gives us 2 times 2 squared, that's 2 times 4, which is 8, minus 2 cubed, which is 8 on 3, and then subtracting 0 minus 0. So in this case, if we'd accidentally left the big brackets, it wouldn't have mattered because we've got 0 over here. But just again, be really careful. Write more down than you feel is necessary in many ways until you become a bit more accurate. Then you can start to cut corners, but try not to cut corners early on. Okay, so we've got 2 times 8 minus 8 thirds. 8 is 24 thirds minus 8 thirds, so that's going to be 16 thirds. And 2 times 16 thirds is 32 thirds. And it's an area, so it is in square units. So obviously each of those regions would be 16 thirds, and then adding them together we get 32 thirds. Okay, example 4, which I think is our final example. Yep. We want to talk about, again, an idea is similar to the previous one in which we want to use symmetries, but this is a different kind of symmetry. Okay, so here we have a log function and we want to calculate this region. Now, if we want to calculate this shaded region, we could, and it would be possible, we could work out the coordinates of this point, the x coordinate of this point, and we could split this into a rectangle here and then a small region between two curves. We'll talk about how to find areas between two curves later on, but we actually shouldn't need to do this. And the quicker way and the simpler integral, and also the other problem we have here is we don't know how to integrate a log function. So we actually can't do this, and it's not a calculator question. So we want to be able to think differently about this. And what we want to do is we want to use the symmetry of the inverse function. Okay. So what we're being asked to do here is essentially find the integral between y equals 1 and y equals 2 of this function. I'll show you a couple of different ways you can think through the logic of this. I'm going to start with it sort of geometrically. So what we want to be able to think about is if we were to find the inverse function, okay, we know the inverse function is a reflection in the line y equals x. Okay, so obviously my graph's not very, well, actually, if I draw it, sorry, I'll draw it more accurately than that. So let's say if I roughly draw in where I think y equals x might be, so if that's 1, if we assume we've got a square scale, let's sort of assume that that's y equals x there, okay? And so therefore this x-intercept here is going to be sort of roughly, it's about 1, maybe it goes kind of there. So let's say our graph, our exponential graph, try again. One more go. Sorry, I aimed at the wrong point. So I want it to hit there and there. That's what I'm trying to make sure it does, and here. So they should intersect on the line y equals x, and they'll intersect again on the line y equals x. Okay. So we think about, that's the inverse function. Okay. We'll work out what that is in a minute. So what we know though is if we wanted, the inverse function is all about switching x and y. So if this is the line y equals 2 and this is the line y equals 1, if we want to find the same area with the inverse function, we're going to look at when x equals 2 and when x equals 1. Okay, so x equals 1 and again it should hit there, x equals 2 just to keep my graph drawn to scale. Okay, so what we're seeing here is actually that this area in here, underneath the inverse function between x equals 1 and x equals 2, would be the same as that horizontal red area that was in the original diagram. So what it means is we need to find the inverse function. So for inverse, we're going to solve x equals log e of y minus 1 plus 2. So we're going to take away 2. And we're going to convert from a log to an exponential, and we're going to add 1. Okay, so now the shaded area that we're after becomes the black shaded area that we've got drawn there, and it is the integral between x equals 1 and x equals 2 of the inverse function. Okay, and so we can work that out. The integral of e to the x minus 2 is just e to the x minus 2 because the a value is 1, and then integral of 1 is x, and subbing in 1 and 2. So we get e to the 2 minus 1, which is 1, plus 2. Subtract, we get e to the 0 plus 1. Okay, so this is e plus 2, take away. Now e to the 0 is 1, so this bracket's 1 plus 1, and so therefore that's take away 2. And so we get e, square units. It's an area. So thinking about how you might be able to make use of the inverse function. The other way this can be thought about, and those who do specialist maths will be more familiar with this kind of thinking. Personally, I think as a methods only student, you're better to think geometrically about using the inverse function and flipping things in the line y equals x so that you can calculate it as an integral beneath the inverse function. But what you can do is you can instead understand that what we're actually trying to do is calculate an integral between 1 and 2 with respect to y. These are y values, y equals 1 and y equals 2. And so therefore, before you can do that, you need this expression to be in terms of y. Okay? And so what you need to do first is your equation is y equals, is exactly what we did in finding the inverse function, because what you actually want to do is solve this equation for x so that you actually have the equation in terms of y. So if we do that, we know that's going to rearrange to be x equals e to the y minus 2 plus 1. And so what you can then instead think about is integrating with respect to y. Oh, sorry, my apologies. Is integrating with respect to y. Ultimately, what you get here is still the same integral. So it's the integral from y equals 1 to y equals 2 of e to the y minus 2 plus 1 dy. And it's exactly the same thing. And the reason that works is because essentially what you've done is thought about the inverse function here. Okay, but those sorts of thinking about use of symmetries, whether that's just literal symmetries or using the symmetry of an inverse function, is really important in being able to calculate these areas. As I said, even if we had learnt about area between two curves back here, we don't have rules to be able to integrate a log function, and so therefore we would have been stuck. So we have to convert it to an exponential function and think about how we can use that. Okay, so the work for today is exercise 11F.